Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, today we're going to continue on two component system. Right, okay, so two component system is system made up of a mixture between two mixture and they have two independent species. Okay, so we can say that the phase structure can be classified into homogeneous and heterogeneous two component system. Right, so if you look at an homogeneous two component system here, the phase structure is single phase, while if you look at an heterogeneous two component system, the phase is having two or more phase come together. So the components are uniformly mixed in the homogeneous. There are in the immiscible actually, they are immiscible. And then this one, the components are not uniform in distant boundary and a line present. Okay, for example, in this case, we have mixture of nitrogen gas and hydrogen solutions. And then we do have a solution of methanol in ethanol, for example, alloy of copper in tin, for example, they are homogeneous. Alloy of copper in tin normally hardly to distinguish them because they are coming from mostly near to be distinguished. Yeah, they are mostly identical. While methanol and ethanol, they are coming from alcohol, so the number of carbons is between 1 and 2, so they are quite um, what we call miscible, okay, to produce a single phase. Okay, while we do have heterogeneous two component system like oil and water that will produce suspension, and that is hard, easily to distinguish between heterogeneous two system here. And then next, okay, right, next, this is how we distinguish miscible and immiscible. So miscibles mean that liquid they are able to mix, okay, for example, or any mixture, all right, that produce like methanol and ethanol just now, they can easily miscible. While immiscible liquids, the liquids are unable to mix where they can produce a distinguished layer between each other, so we can distinguish them easily, right? So these how separating immiscible liquid would be happens. Normally we can do on separating funnel. If you have a mixture of oil and water like this, for example, we can put in separating funnel and shake them together, then we can see that they can produce a distinguished layer between these two. All right, so we can say that this is easily produce heterogeneous solutions. For any miscibility, we can divide miscibility into miscible, partially miscible, and also immiscible. For miscible type, normally they are homogeneous. They mix completely to form a single phase. Okay, for example, ethanol and water. Both are coming having OH and hardly to distinguish them where they mix together because they're entirely miscible. And partially miscible, for example, we can distinguish them by having the distinguishable meniscus between the liquids. The volume is not identical to its original, like hexanol and water. And immiscibles like liquid cannot mix together at all, example like oil and water. The volume is the total volume of the liquid added originally, and or we can find that they're having heterogeneous layer. Okay, right. So solutions and Roots law. Roots law basically states that for any ideal solutions, the partial vapor pressure of each volatile component in the solution is equal to the vapor pressure of pure component multiplied by the mole fractions in the liquid mixture. This is, for example, a solution in homogeneous mixture made up from solid in the solvent. So the solution made up of two liquid components may be ideal or non-ideal. So the Roots law will classify the solution, either the solution would be ideal or non-ideal based on this formula. It says that the ideal solution is partial vapor. Partial vapor is equal to the vapor pressure of the pure component. This one, partial vapor of component A is equal to the vapor pressure of components. Okay, vapor pressure of that component multiplied by mole fraction of the liquid. X is represent the mole fraction of the component A, which is mole fraction means that mole of A divided by the total mole of the total component. Okay, so we're going to look at this Roots law many times later on after this. So the total pressure of the solution is also given by Dalton's law for two components. So for example, if you want to find the total is equal to PA plus PB if you have two components. Okay, if you have only one component, we can use Roots law just now. Okay, so this one, in order to find the total for each of them, we can apply Roots law back here. So P total is equal to PA. PA just now we have looked at from the previous slide. PA is equal to XA P naught A, mole fraction of the A times by P naught A. Okay, total pressure of the A, and then this one PB is equal to XB P naught B. Okay, so we can combine these two Roots law for A and B to find the P total. Always takes notes that mole fraction of A when we combine with mole fraction of B is always equal to 1. Mole has to be, this is number of mole less than 1, this is number of mole less than 1. When we combine together, it will become mole of the fraction is only 1. Okay, so we go back with the Roots law. Roots law said that partial pressure of this of a component is the vapor pressure of pure component multiplied by its mole fraction. So same goes to B. If you have another component which is C, D, E, and so on, the same things apply here. Okay, mathematically we can say that P1 is equal to X1 P1 naught for one component, or PA is equal to XA P naught A for one A component, component A. While for any total, if you have two component, three component, we just time up everything, okay, with the mole fractions and the pressure, okay, pressure. The ideal solution, normally no heat is absorbed or evolved when mixing. The component behave independently in terms of vapor pressure. So next would be we do have two component system, whether the system is ideal or non-ideal. We should know from Roots law. If that solution obey Roots law, that solution is ideal solutions. But if that solution do not obey Roots law, so that solution is non-ideal solutions. So how to know the ideal solutions? So ideal solution basically it must obey Roots law. The ideal solutions are formed when the solid or solvent has similar structure. For example, like benzene and toluene, they have similar ring, 6 ring altogether for benzene and toluene, except toluene having methyl group at the end here. Okay, so the actual vapor pressure of the ideal solutions must be equal the calculated value from both Roots law and Dalton's law. We must say for ideal solutions, P actual, okay, vapor pressure of the actual must be similar with P the calculated. Okay, so that's why for ideal solution, vapor pressure composition graph of ideal solutions could be known as this. In order to plot the graph, okay, we need to have the mole fraction of here, right? And then we have the uh, we have the pressure, okay, pressure of A, for example, from PA towards the P naught A, and from PB towards the P naught B. And this line to this line will give us the P total. Okay, that will be the total pressure of both components. So this is how you're going to plot your vapor pressure components composition graph from A and B. Yeah? So example of mixture that will produce ideal solutions, okay? The one that will follow Roots law is, for example, we have like N-hexane or N-heptane. Both are having methane group, okay? Hexane group or heptane group with N. And then bromoethane, for example, and iodoethane. This is the ethane group as well, all right, with the functional of bromo and iodo. And then like benzene and methylbenzene. Methylbenzene is kind of like toluene, so they have the rings, 6 ring, and then also CH3, okay, at the tail. And then water and methanol. Water and methanol, as I mentioned before, it do have hydroxy group OH. Okay, methanol also have OH. So basically, they would produce the ideal solution if they are mixed together. So these these products or solution basically will follow the Root's law. Right, so this is a diagram of vapor pressure composition diagram of an ideal solutions. Right, so if you have vapor pressure diagram, so basically it shows equilibrium between the liquid and vapor. Right, so this is a mix of benzene and toluenes again. So benzene and toluenes is the ideal solutions that follow Root's law. You can look at this one. Liquid is favorable at high temperature here, P not B, and also vapor is favorable at lower pressure. Right, the composition of vapor in which equilibrium with the liquid mixture composition of C1 is given by C2. So what happened here is actually starting from C1, vapor will be evaporates, okay, and then when you reach the line here, basically it's become equilibrium between liquid and vapor, okay, until it reach this point, dot one, and then it will condense. This part will be condensed to produce more amount of the mole fractions of the XB, for example, mole fraction of the XB will be increased. Right, so just remember that total mole, as I mentioned before, is always 1. Right, so the graph will become either 0 to 1 or 1 to 0, like here. If you read from right to left, XA, mole fraction will become from here to here. But if you draw from left to right, 0 to 1, so mole fraction will become from here to here. Right, so in this case at C1, temperature 1 or percentage of mole fraction 1, this one, for example, we have around 35%. So when it evaporates, okay, as the pressure will be increased, it will evaporates until it reach the end point here, and then it become equilibrium between liquid and vapor. Then it will be condensed to produce more amount of mole fraction for B here. So basically, let's say this is started with 35%, this might be produced around 75% of mole for C2 at C2, yeah. Okay, so this is a real example of a benzene toluene mixture. If you have benzene, mole fraction of benzene, so let's say it start from 0 to 1 mole, right? So it's, again, it start at C1, okay, C1. When the mole fraction of benzene is at C1 in the solution, vapor composition of the benzene is equivalent to point C1, and then it will increase as the liquid composition increase, the vapor composition increase even further, and it produce it being vaporized to produce liquid vapor at this point. So this is the region where it has equilibrium. So make sure you note it down, this one as equilibrium between liquid and vapor, and then it will condense back to produce more fraction of C2. Okay, and another one is boiling point composition curve. Okay, this is the same concept that being applied in fractional distillation. You may look at this one. So you do have, for example, we do have percent of benzene from 0 to 100. If you draw the boiling point composition, it must consist of percentage here, and then for y-axis is always temperature. So what happened here at L1, for example, liquid L1 percentage of benzene, for example, at this point is 5% being heated up. Okay, once the temperature increase until, for example, until it reach around 100 degrees, it become equilibrium between vapor and liquid. This is the region of equilibrium in the middle of here. Okay, until the gases of the vapor reach at point V1, and then it going to condense. While it's condensed here, it will produce L2. So L2 percentage here that been produced will be higher compared to L1. So let's say we start at 5% just now. Now the number become, let's say, around 20%, right? So again, as the process proceed, okay, as the temperature being increased, so again, vaporization will be happen until it reach around T2. Okay, let's say around 60 degrees now. So it's going to produce equilibrium between vapor and liquid around this phase till it reach V2, and the vapor will be condensed to produce L3. So now the number or percentage of L3 that been produced here much more higher compared to L2. You can say around 60%. And the process will keep continue until it finish. Right, so by the end of the process, we can have more percentage of benzene. In this case, we are referring to the benzene. So this process, this concept has been applied in fractional distillation. The same concept has been applied there. So this is a fractional distillation process. Okay, so distillation is a scientific technique that uses separate component and solution mixture by boiling the solution mixture first and then it condense into the vapor. So we can do separating mixture of volatile, okay, based on different boiling point. So using this fractional apparatus, for example, we do have our mixture here, mixture that we want to separate here, right? Has been put in. For example, we do have any mixture of minyak jarak, for example, right? So we can heat it up, for example, with solutions of benzene or hexene, okay, as the solvent. So once we heat up, so the temperature will be rise until it reach, for example, hexene will be start to decompose around 65 degrees. So when it reach 65 degrees, what will happen? Vapor will be produced and it vaporize, okay, to this chamber. So at this chamber, water is coming in and water is coming out. So the process of cooling happen around here. So when the vapor mix with the cooling vapor, the cooling water, so what happen is going to distill and condense. Okay, condense. So at the end of the day, it will be collected and drop here. Okay, drop and collected here at the recovery flask here. So this is all the oil that we want to collect that's coming from pokok jarak just now. Okay, so this is how the process of biodiesel, for example, or any oil separating process that has been done through process of very conventional methods, which is called as distillation process. So again, so this is vapor pressure again. So we do have boiling point compositions, okay, between liquid composition of XA. Okay, so the same thing, this is happen from 0 to 1. So you have to note where your curve will be read out. For example, this is from right to left, okay, XA. So from C1, it will be heated up, okay, until it reach this point, and then it's going to evaporate. We're going to be equilibrium between vapor and liquids until it reach D1, and then it's going to condense. And the process will repeat to reach equilibrium and then condense. So the process will repeat again and again until the process is finished. And by the end of the day, the number of mole of fraction will be increases here. So this is another example of water alcohol system. So figure shows a boiling point composition graph for water alcohol systems. This is example with water and ethanol. So methanol, sorry. So percentage of methanol at the beginning is 20%. So when the temperature has been increased, vapor will be increases as well. It evaporates, okay, to produce the vapor until it reach 90% here. Okay, and then it's going to be equilibrium between vapor and liquid. You have to state the equilibrium between vapor and state condition here until it reach point E, and then it's going to condense until it's going to reach point F, or this is around 30% of your 40%, let's say, and then going to be heated up again. Okay, all right. Process of equilibrium will be happen here until it reach point G, and then condense again. This one at this point might be the numbers or percentage methanol is around 70%, and then it's going to evaporate again, equilibrium and condense until the process is finished, right? So the concept, just like fractional distillation that as I mentioned before, okay, that is happen in ideal solution. For non-ideal solutions, right, the low concentrations of solute mostly shows a deviation from the ideal solutions. Non-ideal solution is deviate from ideal solution in two ways. The positive deviation it must have positive deviation from Roots law, or it do have negative deviation from Roots law as well. So how does this happen? So look at this one. For any positive deviation for non-ideal solutions, the attractive forces happen between A to B, lesser than A to A or B to B. So pressure is higher than calculated in using Roots law. The volume of the solution is more than the pure compounds. The enthalpy of solution is positive. So for example, water ethanol mixture or propanol carbon disulfide. But for negative deviation, okay, the attractive forces happen between A to B is more than A to A or B to B compound. Pressure at total is lower than calculated using the Roots law, and the volume of solution is less than pure. Okay, so the enthalpy of the solution would be negative. So this is the diagram of the positive deviation and negative deviation. So remember, this is positive deviation and negative deviation that happen only for non-ideal solutions. Okay. So positive deviations, you can see the graph is much more look like smiley smile. Okay, they're very positive, so it's smile. Right, while negative deviation, the graph is tend to be like sour. Okay, it's not smiling. Okay, masam kat sini. So positive deviations, the total pressure of the solution of two miscible liquid is higher than calculated, while this one, negative deviation is lower than calculated using Roots law. Boiling point is lower, so look at this one, the boiling point is lower than its pure solutions, while this one boiling point is higher, okay, than its pure components. So in this case, in order to determine which one will be distillate and which one will be the residue, we need to remember that we need to know that in this case, azeotropic mixture will be the distillate, because once the pure substance is being heated up, so it's going to be evaporates, equilibrium, and condense, and the process will be continue. But somehow it's much more nearer to the azeotropic mixture here. So the one that will be distillate first is azeotropics, while residue, which is a pure liquids, will become the residue. Okay. So for distillation, distillate, this one for negative deviation, distillate will be pure liquid. Okay, right. Distillate will be pure liquid, as this one happen as well. So evaporate, equilibrium, and condense. Alright, so distillate is a pure liquid itself, while residue will be the azeotropic mixture, because it's still far from the azeotropic mixture. This one I'm going to explain it in class with the draw of the sketch diagram, in order to ensure that you are more understand on this part. So okay, so you can read on azeotropic system here. Okay, so positive deviation and negative deviations. Okay, in order to understand it better, you must draw this one. Okay, component of azeotropic mixture. So for example, we do have propanol and trichloromethane. If you are given these two components, okay, and you may try the rest as well. So you are given a normal boiling point, okay, for each of them, propanol and trichloromethane, the normal boiling point, and mole fraction. If you are given some information like this, so how are you going to interpret it to become a diagram? Okay, so you must look at the number of boiling point here, or azeotropic boiling point here. Does the azeotropic boiling point is lower compared to normal point, or does it higher compared to boiling point? This will give you some key point on answering the question to determine whether the structure, okay, the graph would be positive deviation or negative deviation. If you have lower boiling point compared to other, for example, this one is the lowest, so it means that the graph will be smiley graph, positive deviation, because boiling point is at here, right? But if you have the most highest temperature like this, okay, so it means that you're going to have negative deviation, where the point of temperature is at the highest. Okay, so this is your graph, azeotropic mixture, and then this is your graph. Okay, and then compare this one. This is also the highest one. That will be the negative deviation. Okay, negative deviation, you may draw negative deviation. So this is, okay, this is positive deviation, the lowest one, and then this is also negative deviation. So I want you to try this one, isotropic mixture. Okay, sketch the deviation, whether the deviation is positive deviation or negative deviation for two component system with the mole fraction of this being given. Right? Okay. And then we're going to discuss in the class later on. Okay. So yeah. So these are a part of the answer. Okay, so do the exercise here as well. So answer being given. So we have looked at on one component system, two component system, and also we have looked at on which one obey Root's law and which one do not obey Root's law. And that happened for boiling point. For any melting, we talk on eutectic system. So eutectic system is actually mixture of two or more phase, okay, at a composition that has lower melting point. So when we talk about melting point, we talk about eutectic. So liquid normally is going to freeze at minimum temperature. So normally, okay, right. So when it freeze, become crystallized, okay, from the molten solution. Proper ratio normally is obtained in eutectic, is identified as eutectic point. Okay, so the term words from eutectic is coming from the Greek word which is eutectos, meaning easily melted. Right. So this is a molten solution is actually solution formed at liquid phase where you do have high temperature. Okay. Right. So look at our eutectic system. Okay, eutectic systems can have either eutectic mixture or non-eutectic mixture. Eutectic mixture means that the mixture are equilibrium. So liquid mixture will be freeze at minimum temperature, while non-eutectic mixture normally none of them are become eutectic mixture. Okay, so this is eutectic diagram. Okay, eutectic diagram. So for example, eutectic diagram, okay, you're going to have a phase, you're going to describe between alloy, for example, two component, they are completely soluble at liquid state and they're entirely insoluble at solid states. So basically the graph will be have temperature graph, left and right. This is temperature for component A. This is temperature for component B. So normally we're going to have like two component, okay, whether stannum or plumbum and then cadmium or bismuth, for example. Okay, and then this is the concentration. Okay, all right. So what would happen here is it's going to melt. How the component going to melt from one point towards another? Just a straight one. Okay, for example, when it have been heated up at T1, okay, when we reach at T1, it's going to melt and produce component 1%. And then at T2, it's going to melt and produce another component 2, and then so on and so forth. That is happen for example, for stannum, here. And then for example, plumbum, for example, is going to melt as well as the temperature increase. This plumbum will be decreases, the plumbum will be melting and produce another 0.% of plumbum itself. Okay. So eutectic point, okay, is the point of phase diagram where maximum number is allowed. Okay, there are reached temperature, mostly there are constants. All right. So liquid normally with eutectic composition freeze at single temperature without previously depositing. Solid with eutectic compound normally they melt without change the composition. Okay, at the lowest temperature. So for example, like solder, okay, so you do have composition of 60% of tin and 30% of lead, where they mix between two mixture here, and they melt at 183. Okay, so this is what I mean by two component, okay, melting together. For example, this is between zinc and cadmium. So this is cadmium percentage. This is would be zinc right? So first, so when we have cadmium here, so basically we can presume that this is 0 cadmium, while this is 100% cadmium. So once it has 100% cadmium, so this is a graph of cadmium. Okay, so this is the peak of this is the axis of cadmium periodic, and then this is okay. So means that the other one would be zinc. Okay, this is would be zinc axis. So what happened here? Okay, what would happen here is actually when pure liquid of zinc is cooled, it's freeze at 419. Okay, so the amount of cadmium is added to zinc and heated to it become liquid. So when it's cool, it becomes solid, both will become solid and freeze at lower temperature than pure zinc. Alright, so adding more cadmium will cause freezing point to drop further, and finally they reach at 270. They reach together at 270 and they melt together at 270. So at this point they will reach percentage of cadmium, which is for example 70% here. So means that you do have 17% of zinc and 83% of cadmium here. Yeah? Okay, so means that cadmium will be freeze at 321, while zinc will be freeze at 419. And then when the temperature drop, they will melt together to produce the lowest temperature, which is the lowest temperature is 270. So that's point when they reach at 217, this point is known as eutectic point. Okay, so eutectic point is the lowest point that it can melt. Okay, that's its eutectic point, right? So next is on cooling curve. Cooling curve is a line graph that represents the change of phase, typically from gas to a solid or from liquid to a solid. So this is a cooling phase. Not all material having the same cooling phase. Some of them could have different kind of stagnant or different kind of curvy part. Okay, so it depends on variable of x, okay, in time, and it depends on temperature as well. So this is cooling curve for non-eutectic mixture. For non-eutectic mixture, if you have two eutectic mixture from A to B, okay, it's cooled from A to B. So basically the slope are changing like this. Okay, firstly, liquid will be cold. Liquid A will be cold at some temperature until they reach temperature B. So once they reach the temperature B, solids will begin to appear. And then solid and liquid will reach equilibrium from B to C. And that is the point where there will be reach the eutectic mixture together and become freeze. Okay, and then solid will be cool. So this is the non-eutectic mixture for any cooling curve for non-eutectic mixture. If there are eutectic mixture, they can have two graphs like the eutectic mixture just now. Okay, so this one has to be memorized. So normally this question coming in as well. Right, so this is example of cooling curve for non-eutectic mixture like bismuth and cadmium. Right, so you can see that curve L and F, this is curve L and this is curve F, slope change at point of P and Q, okay, due to the precipitate formed during the cooling process. Heat release from the substance, the cooling process slow down and the slope decline. This is what happened during the process. And when the heat is released, the heat is called as heat of fusion. Okay, heat of fusion. So there are three sections of the graph. The first section of the curve, normally the liquid is cool and reach supercool stage before the freezing takes place. And then you're going to see that some region are plateau or stagnant. So when it has plateau region, so meaning that freezing occur where the temperature remain constant until all liquid turns into solid. At this point, temperature is freeze to form liquid and it melt. Okay, and the last section, solid is cool from the room temperature. Okay, last but not least topic is on colligative properties. Qualitative properties, it means that a solution may form from solid and also liquid solvent. The solution form may have known as qualitative properties if they have vapor pressure of the solution is lower than vapor pressure of the solvent and boiling point of the solution is higher. Okay, the freezing point of the solution is lower than the freezing point of the solvent. So let's look at boiling point elevation, or the other point is freezing point depression. So for qualitative properties, it's only happen on these 2 points, okay, boiling point or freezing point. So boiling point elevations means that liquid boil equal to the atmospheric pressure. Boiling point is constantly inversely proportional to the vapor pressure. So T boiling is known as TB is equal to TB solution minus TB solvent. That is equal to KBM. So KB is a constant elevation of the boiling point and M is the molality. Okay, we have seen this in the lab before. Okay, TB is equal to TB solution minus TB solvent, but we do calculate for freezing, KFM, if you still remember, TF minus TFB solution is equal to KFM. Okay, this is example how to calculate KB. Okay, KB using this formula, delta TB is equal to TB solution minus TB solvent. So we are giving 0.0.1 mole sucrose dissolved in 100 grams. So this is can find molality. Okay, and then calculate the boiling point at 1 atm. KB is given. So TB of the solution is 0.51 degrees Celsius. Okay, and then solvent is equal to 0.01. Okay, divide by 1000 gram, 100 grams. Okay, to convert into kg, so that will give us the TB. Okay, and then TB solutions, if this one, okay, 0.0512 plus 100, that will give 100 degrees Celsius. Okay. All right, this is KB. This is KB value, and then M is molality. Right, that will give us delta TB. So delta TB, as we know, boiling is happen at 100, so we need to add, okay, 0.05 at 100. So that will give us 100 point something for T boiling of the solution. Okay, for freezing point depressions, freezing point is always depressed because freezing point is decreasing. Okay, so freezing point of the temperature is happen when the solid substance are equilibrium between liquid and solid. So this one, the formula is TF is equal to TF solvent minus TF solution is equal to KFM. So freezing point elevation constants, okay, KF, and molality is still mole of the solid over mass of the solvent. So example, 0.01 sucrose dissolved in 100 gram water. Calculate the freezing point of the aqueous. KF is given. So we use the formula delta TF is equal to TF solvent minus T solution equal to KFM. So KF is equal to 1.86, okay, times by M molality 0.01 mole over gram to convert into kg. That will give us delta TF. And then for every freezing must be liquid freeze at 0 degrees. So whatever you have answer here, it must be minus from 0. Minus your answer, that will give the minus TB solution. Okay, then only freezing happened at minus for TB solution. Okay, so that's all for our topics. We will do the tutorial. We will discuss the tutorial on next week. Thank you very much.